Okay. Hi, thank you very much. And for this opportunity to present here. So this is really representing a large group's work, especially Yunyao Li, who is a former postdoc and research scientist in my group. Now she just become her journey as a research assistant, assistant professor at University of Texas. This work was really motivated by an earlier work done by our group, try to simulate the 2017 campfire in California. So we use 112 numbers of ensemble trying to simulate that PM2.5 from wildfires. What we found that this ensemble has really a large spread from one simulation to another simulation. The surface PM2.5 concentration can vary by a factor of 1,000. And most of these uncertainties or the spread was caused by emission data sets. In this case, we only use 4 emission data sets and plume rise, as well as metrology and the transport options. So here I only have time to cover 2 of the uncertainty sources, which is emission and plume rise. So my actually the cases had already been explained by the previous speaker. Thank you, Aihua. The first case we are going to study here is the 2020 Western U.S. fire, or also Gig Fire. This is you can see that this is the GEO6 taken this video from the live website I also watched, developed by Schubert's group. Almost the entire United States was blanketed by those fires. And if you look at the long-term trend, 2020 really stands out. So this fire burned more than 1 million acres of land over California and Oregon, other states. And the fire was a primary contributor to 3,700 observed exceedance of the national ambient air quality standard for PM2.5. That was really unseen before in the United States. So for this time period, we compare 11 data sets, that's including the Environment Canada and Environment and Climate Change Canada's GFIPS data sets, the UCMWF, GFAS, US EPA, which is the only, well, it's not the only one, and it's the other one. FIN is also kind of bottom up, but the EPA was using the blue sky, so it's very unique in that they consider a lot of ground conditions. And NASA, we use 2 data sets, and there's FEAR and the QFET. And NCAR, there's FIN developed by Christine and colleagues. And we also use the Naval Research Flambe by Edwards and colleagues. And NOAA, we have 3 data sets. That's 4 data sets. That's the GBBX you heard before. And REEF is this blended global polar orbiting and geostationary data set is hourly, unique in that. And we also have HER smoke, which is only use smoke as a tracer. So it's not represent the total PM2.5. Keep that in mind. And RAPCAM is another one for NOAA. So we first did a comparison for the global, for all the data sets net with the global coverage. We found that surprisingly, the differences are pretty small within a factor of 3. Remember, this is for about 1 decade, 10 years comparison. And if you look at the global differences, the highest one is GBBX, and then those ones are GFAS, but that's only like a factor of 3 difference. The black one is the ensemble mean, which we blended all the data set together, trying to come up with this ensemble emission data set, just as a reference. However, if you dive into North America, you can see the difference is much larger. That the different, in general, there are the RAP is smaller, and HER, I think it is HER is only representing a portion of the PM2.5, and the other products are generally higher. So if you look at the daily differences, it can reach a factor of 10 and sometimes to 33. So this is a really big difference. So where do you got this uncertainty from? Where do you have the differences? There are three, you consider all the emission was derived by essentially two factors, right? One is emission factor, another one is dry mass burned. So all the tricks are either in the emission factor or in the dry mass burn. So we look at the emission factor because this is a pretty simple one to look at. This is the emission factor from all data sets for temperate forest fire or wildfires. You can see that the difference for PM2.5 is less than a factor of 2, right? It's pretty small. And CO is even smaller, and NOx is the same. So you do not see a large difference in the emission factors, mostly by a factor of 2. And you can look at the agricultural burning. This is pretty common in places that that's in a certain recurring sources, right? And this you are seeing more difference, especially for some models like the Canadian models, and they have a different emission factor used. But in general, all other data sets are pretty close to each other. So our conclusion here is emission factor is not a major source. It's not going to give you a factor of 10 or 30 difference. The major difference will be in the fire detection and the fire reductive power. And another factor that's contributing to air quality, because I'm an air quality modeler, is the fire injection height. So fire is very different from other sources. It's not always emitted at the surface. And we are using the 2020 Canadian fire mentioned by Aihua earlier, because in this case, it's very unique that the fire source was in another country, and the US got a lot of incidences of air quality. Almost 70%, more than 70% of the PM 2.5 incidences was attributed to the fires outside the US. So we have implement 3 plume rise schemes. One is the BRICS one. Currently in the community multi-scale air quality model is the air quality model we use. And we add a FRITAS 27 as from the WolfCam model. And also based on Mahil's work, we added the SOFAV 2012 scheme. So we put all the schemes into the same model and run the model and extract the top of the aerosol layer and compare that to the miser aerosol height retrieval was given to us by RAFCAM. So we found that injection height generally is BRICS give you more height for this case, okay, and followed by SOFAV and the FRITAS. And you at the bottom you are seeing the comparison of these simulations during the complex fire. There are 2 fires. One is a northern plume, another one is a southern plume. Essentially, you have the highest one from BRICS. Actually, in this case, especially for the southerly plume, the BRICS is giving better results. But for others, SOFAV is doing better. So what is the impact of plume rise scheme on the surface PM 2.5 exceedance prediction? Again, we put in these simulations for the 2020 gig fires. This color scheme is if you have red, that means only predicted by SOFAV 2012, blue by BRICS only, and yellow is by FRITAS. And you have different colors if more than one scheme predict exceedances. Over a large region, all the 3 schemes can predict the same region, but however, further downwind, such as in the eastern United States, in the case of the Canadian fires, that the plume rise, the choice of plume rise really stand out. So to wrap up, that fire emissions is contributing increasingly to exceedances of air quality standards in the United States. And the difference among the 11 data sets that we have chosen to examine vary by a factor of 10 to 33 during the gig fire. And we found that emission factors are relatively stable. So the difference, the majority of the difference are attributed to FRP and fire detection, which is something we have to consider when we transition to the new sensor. And plume rise and injection height play a major role for transport smoke, which is also important, not in emission per se, but for air quality forecasting is really important. With that, I want to thank all the people in the audience and then also the people who contributed the data sets and code to us. Thank you.
Thank you so much. Thank you for your nice presentation. Now we will remove for vacation step. Someone vacation. I saw the hand of Elindo das Silva. You have the floor.
Yeah, Elindo, please go ahead.
Elindo, you are in mute. Okay, we will give.
Can you hear me now?
Yeah.
Yes, now.
I use Zoom, so my mic was completely. Quick question, two basically questions, Daniel. One is the statement about emission factor, right? QFED does not use emission factors for aerosols, right? Is a FRP base is usually some kind of tuning, right? So I'm not sure exactly how I was able to compute. So it makes probably more sense for the bottom-up algorithms to compare emission factors. Once you are in the FRP, what's usually called emission coefficients, and it's not an easy thing to compare across, right? So I'm not so sure. So, but regarding the plume height, did you look at the cases where we're not exactly the mega fires, right? The things where some of those schemes tend to elevate the plume when in fact they're not. Did you have a chance to look at the false positives?
False positives of what?
The fires, they are not really elevated, right? And that in fact, you are not really, some of those schemes that tend to elevate, the plume when in fact they are not. And typically for the very strong fires, you would have something with enough oomph to leave the boundary. I'm just wondering if our analysis of plume rise also was extended to no extreme cases, because that sometimes can be a big problem.
Right. So first of all, on the QFED, I think I agree that different top-down and bottom-up using different approaches. But if you look at the approaches, essentially boil down to dry mass burning. They're using FRP plus times beta, give you the dry mass, but they also need a emission coefficient or emission factor. So that's why we did in that comparison. Not everybody providing the data sets. And so that's what we included in the one we had available from us. Back on the question on plume rise, this is really some work we just got started. I don't think we have a very conclusion on how well each scheme is doing, especially if you really need a fire weather model to do that when you have a large fire, for example. It's completely changing the meteorological conditions. So you will need a two-way feedback to be able to calculate right. I think FreeTask is the one supposed to be doing that work, but surprisingly, for some cases, they're not necessarily the more complicated code or to be doing better. For example, the SO5 code is like 209 code that I basically wrote and got help from Mihail. Now we implemented, but the FreeTask is like 2009 of code. It's still very complicated, right, to get it right. So for the false positive, you will need a good data sets. So we are really looking for good data set. When Ralph Kahn was at NASA, we just got a lot of help from him. He sent us all the cases we can find from Measure. So we are very excited by the new aerosol near height data sets and to see if we can use that. Another one we are trying to do is get the weather data, weather radar data. That's something we are exploring. But in general, we have not got any good results beyond what we have reported here. There's going to be last Earth Venture, right? Earth Venture 4, so they're going to look into this. They will see where they can find.
Thanks, Daniel.
Okay, Christine, you have.
Hi everyone. Thanks, Daniel. That was awesome. I just had a question. I mean, you mentioned like this is not emission factor. It's based on like the biomass burn, which of course is also a function of the fuel loading and what's burning, like the type of ecosystem. So, and that's true regardless of whether it's a bottom up or if an FRP based, because FRP still makes an assumption of the biomass and the ecosystem that's burned. Is that correct?
I think so. It's using the energy, to represent the dry matter.
Yeah, there's no assumption, right? So it's basically the energy that you measure, of course, is a function, but that's not a one input, right?
It's not.
No.
Okay. Okay, but like if you have an FRP in a grassland and an FRP in a forest, when you have different emission load, like emissions totals or no?
That's right. But the amount of, it's how much, wood that you burn to create that energy, right? So now the kind of gases that's going to be emitted is going to depend on the type of combustion, right? The modified combustion efficiency. And so those are the things primarily that's going to, control it. But, basically it's like the FRP that you measure from above is a witness, of how much was there to be burned, because it is burning. Right? It's the amount of energy is related to the amount of mass being consumed.
Okay, well, thanks for doing the study, Daniel. I think it's great.
Thank you.
Okay, thank you. Sandy, you can.
Hi, yeah, thank you. I just saw CFEPs in some of your results, but did you didn't include the CFEPs plume rise in your plume rise stuff? Are you planning to in the future, or to intercompare the CFEPs plume height scheme?
Yeah, we have published the preliminary results, and the code has been implemented in the CMAQ model. So we have sent, at least we sent to EPA for the code. I'm not sure we're not going to implement it in the public release. But if anybody is interested, please contact us. We can send you the code.